cannot focus, then you can do whatever you need to do. Okay, so I'm gonna start Unit 2 solutions, and it starts with the molarity. All right, let me see if the pen is working. Okay, great. Remember, I told you that this video is going to be posted on eClass for you to watch it later, and the key will be also updated in the eClass, so you can also look at it later. Okay, so 2.1 is molarity question. We have fill in the blank question for molarity. Let's go through them. So molarity is a measure of the number of the solute particle in a solution. Okay, if something has a high molarity, that means there are lots of number or high number of solute particles. Molarity is a ratio of, let me see, moles of solute to the liters of total solution. The formula can be rearranged in 3 different ways. So N is equal to mole over liters. The moles are equal to, let me see. Moles are equal to molarity times liters, or liters are equal to mole over molarity. So there are 3 equations. Okay. So the questions that you will be asked to do for molarity is to find the M of a solution prepared by dissolving 100 grams of BCl2 in a 2.1 solution. So we know our, let me see. We know our given is 100 grams and 2.1 liters. So that's something that we need to write. We need some space. Should be okay. Right. Going back to the question. Okay, what is the molarity of a solution prepared by dissolving 100 grams? Okay. So we know that it is, our given is 100 grams of BeCl2 and then 2.1 liters of a solution. And then we're looking for the molarity. So we know that we'll be using equation M equals to mole divided by liters, but we don't have the mole yet. So what we'll do is we will convert the grams to the mole. So step 1 for this question is grams to the mole. So calculate the molar mass of the substance that is being dissolved, which is BCl2. So it will be beryllium is, you have 1, and then you have 9.01 grams per mole. Chlorine is 2. So 2 times 35.45 grams per mole. So it would be 9.01 and then 70.9. So if I add those two, These will be 79.91 grams per mole. Then we change the grams to mole by dividing the given 100 grams by the molar mass. Which will be 1.25 mole of BCl2 Then step 2, you will use the formula. Which M is equal to 1.25 mole over 2.1 liters, and that's gonna be 0.595. So this one will be 0.60 molar solution of BCl2. So that will be your final answer. And that's how you would do this problem. Yeah.
Me,
Can I?
you have taken notes.
7.9.
Yeah.
Like 8.
Yeah. This is almost 80.
It doesn't matter if it is like too close.
Yeah, it's okay. We can get to like the 2 decimal points. Yeah, so that's fine. James, what? Did you ask me something?
You have taken notes.
I do.
I get some.
Yes. Okay. Here. There we go. Just one.
What they are? Can I get like 3 more? What is the option? Formula.
Huh?
What formula? Thank you.
All right, now we're gonna move on to 2.2, which is solving for volume or moles. And we wrote down these formula up there. But if you're looking for the volume, which is liters, then it will be mole divided by the molarity. If you're looking for the moles, then it will be M times L. All right, so question says, what is the volume in liters that is needed to create 3 molar solution with 1.5 moles of FeCl3? So since we have this in moles, we don't have to look for our molar mass. So what's gonna happen is we're gonna use this formula where it says liters equal to mole divided by molarity. So we have 1.5 mole of FeCl3 and then divided by 3 molar solution. So 1.5 divided by 3 is giving me 0.5, and that's the unit will be the liters. So the second type of question would be maybe simpler than the previous one. So that's the molarity. Okay, I'm gonna move on. Can I move on? Okay, I'm gonna do the percent by mass. So percent by mass is a percentage of and that is in a total solution. Percentage of solute that is in total solution. The solution is made up of two parts, the solute, the solvent. No. The solvent is this one. Usually water and then solute. Is that something is dissolved in. So percent by mass would equal to mass of solute divided by mass of solution times 100. Okay, and then remember that mass of solution is equal to mass of solute plus mass of solvent. So whenever it says the 300 grams of water, then we know that this is going to be the solvent, the mass of solvent. So we will have to add the mass of solute with the mass of solvent to yield the mass of the solution. Okay, so we know that the mass of solute is 150 grams. So percentage will equal to 150.0 grams over 300.0 grams plus 150 times 100. And the reason why I added those two was because 300 grams of water was the mass of the solvent only. So 150 divided by 300 plus 150 times 100 is equal to 33.33%. Okay, so I think that's okay. How you would solve this question. All right, now question 2 has a different type. This one is going to give you a total mass of 750 grams. So if it says like total mass of blah, blah, then that one would be the mass of solution. Which means it's not going to be, we're not going to add 500 to 750. So it says, what is percent by mass of a solution that contains 500 grams of CaPO42 in a solution with a total mass of 750? So this 500 would be the solute. And then 750 would be the total mass. So that will be the bottom number. So 500.0 grams over 750.0 grams times 100. It will be 66.67%. All right, so that's gonna be the percent by mass. Just pay attention to the last word. If it says water, like water right here. Water, then that's the solvent. Total mass is the solution. Those are the key to know the difference. Okay. I'm gonna move on to solubility conceptual. All right, so solubility measures the maximum amount of solute that can be dissolved in a gram amount of solvent. If a solution has dissolved less than maximum amount, then it is considered to be a unsaturated solution. If it has dissolved a maximum amount, then it is considered as a saturated solution. If more than the maximum amount has been added to the solution, then only the probable maximum amount will dissolve and the rest will sit precipitated at the bottom of the container or undissolved at the bottom of the container. All right, so question 1 says George is trying to create two different types of solution in a beaker A and a beaker B. You have a beaker A and beaker B. There is a water that already contains 10 grams of salt. He adds 20 grams to beaker A and it all dissolves. He adds 30 grams to beaker B and only some of it dissolves. How should he label the type of solution in beaker A and B? Okay, so the situation is you have beaker A. We have beaker B. And then we have some water. And then we already know that there was 10 grams of salt. Okay. So he added 20 grams and it all dissolved. If he added 30 grams, then some of them is left undissolved. So because beaker A dissolves everything, but beaker B doesn't, what will happen is beaker A will be unsaturated. And then beaker B is saturated. That's why you see some salt that is not dissolved at the bottom of the container. Okay. Okay, question 2. The solubility of a mystery solid is 45 grams per 100 milliliter of water. Label each of the following solution as either unsaturated or saturated. So I will label unsaturated as U and then saturated as S and determine the amount of solute that will not dissolve. Okay, so if something has a solubility of 45 grams, then that means it can dissolve up to 45 grams. So anything that is under or at 45 grams are going to be unsaturated So A would be unsaturated. F will be also unsaturated. But if you're at 45 grams, then that one would be saturated. So B will be saturated, but all of them is going to dissolve. C is also saturated, and 10 grams will not dissolve. All right, 60 and 74, both of them will be saturated solution. And then 60 minus 45 will be 15. So 15 grams will be not dissolved. 74 minus 45 would be 20 something. It's just 29. So 29 grams will be undissolved. Okay, so that was question 2. Okay, if this doesn't make sense, don't worry. How did the question look like with that one? Let me double check. But it's pretty simple. You take the solubility number and then compare it to the amount of salt that is put in. More than that. All right, next one is a solubility graph. Okay, solubility graph can be plotted by solubility on the y-axis, so solubility, and temperature on the x. Nothing. You are walking towards me. If the line has slope upwards, the solute is going to be a solid. But if it's sloped downward, it is going to be a gas. Its line represents the solubility or the maximum amount that can be dissolve at that particular temperature. If a solution is created with less than that, it is unsaturated. If it has more amount as a line or more, it has the same. It is saturated. And you see the solubility graph on the left.
Oh.
No, on the right. Ah.
Todos los días me estás diciendo, todos los días trabajando.
¿Dónde van? Ay, no. Si yo les trabajo,
Okay. Okay, it says, the question one says, what is the solubility of KNO3, which is the green line right there, at 50 degrees Celsius. So 50 degrees Celsius is right here. And then if you go up to where it meets the line, it's about 86. So we'll just call 86 grams. Question two, how many grams are required to create a saturated solution of NH3 at 10 degrees Celsius? So NH3 is the purple line right here. No, blue line right here. So at 10 degrees Celsius, it's right there, about 71 grams. So you will have to add 71 grams of NH3 to make a saturated solution. Question three says, how many grams of NaCl needed to be added to a solution that already contains 10 grams dissolved in order to create a saturated solution? Where is the temperature? Oh, okay. Well, let's assume the temperature is going to be 30. So if that's the case, NaCl is going to be right there, which is 35 grams. And we already have 10 grams. So 35 grams minus 10 grams will equal to 25. So we can dissolve 25 more grams to make the solution saturated. Okay. Question number 4 says, how many grams of KCl3 will remain undissolved if 20 grams are added to solution at 20 degrees Celsius? Okay, so at 20 degrees Celsius, it's right here. So it's about 5 grams. And then we put 20. What you will do is 20 grams minus 5 grams, which will be 15 grams. So 15 grams will be remain undissolved. Oh, that's 80. Good. Hang on, let me take the attendance. Okay, let's figure out these blank. Okay, not all solute will dissolve at the same time or at the same rate. The rate that the solute will dissolve depends on if it is a polar or non-polar, but that's the word that we didn't learn. Okay. And oh, okay, it's if it's a solid or a gas and the various factor. In order to increase the rate of solid, you need to increase the number of collision between molecules. These are 3 factors that affects the rate of solid. Temperature, stirring, and surface area. There are two factors that affects the rate of gas, which is pressure and temperature. The temperature measures the average kinetic energy or speed of the particle. Solids will need a high temperature to dissolve quickly, but gases will need a low temperature. The larger smaller the pieces, which means solid needs a large surface area to dissolve quickly because it will increase the number of collision. Okay. Okay. Question number 1. I think I'm going to type in more reasons. Going back to this mode. Okay, here is the rest of it. If you didn't get it. Okay. So solid more needs a lot of inflation to dissolve faster, while gases need less collision to stay dissolved. I temperature more collision is the lower less kinetic energy Okay. That's the reason, but you can copy it. Or let me briefly explain this part. Okay, so solid is really different from gas. Gas is a phase where the particles move really, really fast. Solid is like the opposite of the gas. So in order to dissolve solid, you want to have high or large number of collision, but gas behaves the opposite way. So gas wants to escape the solution. Therefore, you want to limit the number of collision, or you want to limit the energy that the gas particles have. So that is why if you want to dissolve the gas, which is like, imagine soda or Coke, any kind of carbonated drink. If you want to have a lot of carbonation inside of the drink, then you want to keep the Coke or the sodas in the refrigerator, which it has very low temperature. So it's kind of preventing the gas particles to stay inside of the solution versus if you're trying to dissolve like a hot chocolate powders are solid, and you increase the temperature of the water by boiling it, and then you dissolve it into the hot water instead of cold water. So that's the difference between the solid being a solute, a gas being a solute, and that's the different way you dissolve those two faster. If we make a comparison. Alright, so that's what I am basically saying in question number 1. So solid needs a lot of collision to dissolve faster, while gases need less collision to stay dissolved. So the higher the temperature, more collisions, and the lower the temperature, less kinetic energy equals gas molecule tends to stay in the solution. So that's why 80 degrees Celsius for solid would be the best. 50 degrees Celsius would be the best for the gas. But actually 50 is still high. It's like higher than body temperature. That means near 0 degrees Celsius would be perfect for the gas. All right, question 2, it says what or which solid will dissolve the slowest? It says the slowest according to the data table below, and explain why. So we have to pay attention to if it's going to ask you about the slowest or the fastest. So we have experiment A and experiment B. Since this one is solid, we want the temperature, well, they're the same, so it doesn't matter. We don't want to stir because we don't want it to dissolve fast. Surface area, it needs to be smaller. So the experiment B will be slower because no stirring means less collision. Small surface area. Oh, actually, let's add those two. No stirring and small surface area means less collision, means slower. All right. And then the question 3 asks you which gas. It says gas will dissolve fastest according to the data table. So I want my temperature to be low, pressure to be high. Temperature to be low, and then pressure to be high. So the 10 degrees Celsius is lowest, and my pressure, if I compare these two, 15 would be higher. So therefore, B would be the correct one. Low temperature and high pressure will prevent gas particles or molecules from escaping the solution. Wow, finally we're at the last section. Okay. So when compounds, okay, the last section is about solvation and dissociation. So what I'm going to tell you is if you are able to distinguish between the covalent compound and ionic compound, and you're able to tell me the difference between solvation and dissociation by using this part, then you will probably get a full point on that particular question. Okay, so here we go. When compounds dissolve, there are two possible processes. The first one would be solvation, and dissociation will be the second part. So solvation is when the particles dissolve and the water surrounds them. This happens when all compounds dissolve, both ionic and covalent. Dissociation is when an ionic compound separates into cation and anion. Because the water is polar, the hydrogen have a partial positive charge and the oxygen has a partial negative charge. The cation is surrounded by water that is rotated, so the hydrogen, no, that is oxygen. Atom is near it, while the anion is surrounded by water that is rotated, so the hydrogen atom are near it. Actually, I will write H. Oh, right there. Okay, question 1 says label each of the following as either ionic or covalent compound and if it will undergo solvation, dissociation, or both. Okay, so ionic is when you have metal cation, and covalent is when you have only non-metals. And then you look at the periodic table to figure this out. Okay, so NO2, they're both non-metals. So this one is covalent compound and it will experience only solvation. Okay, same thing for CO2, covalent compound, only solvation. MgCl2, Mg is the metal. So this one is ionic compound, so both. NaPO4, Na3, this Na is metal, so ionic, which will experience both. Carbon and fluorine, they're both non-metals, so it'll be covalent compound, only solvation. COF2, CO is a cobalt, so that's the metal, which means it's an ionic compound, and it will experience both. Restroom? Okay. Okay, hopefully this one is last. Is it? Yay. Okay, number 2, question 2 says describe how each of the following pictures specifically shows their either solvation, dissociation, or both. Okay, let's look. Okay. All right, so if I look at these, all right, I think the picture one, you have a sugar, and then C, H, and O, all these three are nonmetals, which means they are covalent. Compound and sugars are usually covalent compound. Therefore, picture number one is only showing you the solvation. And as you can see, these are not, it doesn't have positive or negative sign. So it will be showing you the solvation only. Picture two is showing you the both, because you see that the positive and negative are being dissociated right there. So it'll be both the solvation and dissociation. And I think I'm gonna kind of verbally explain. Yeah. So solvation is when water molecules are surrounding the sugar or any kind of solute particles. So if you see solute particle that is being surrounded by these water molecules, then that's definitely a solvation. So solvation happens before dissociation. So the water molecules are surrounding the salt crystal. So there you see the solvation. And whenever it detaches these anions and cations, then that's you see the dissociation. So this part of the diagram is showing you the dissociation. And as you can see, the hydrogen is partially positive. So that's why it is facing the anions, which has negative charge. Oxygen is partially negative charge. That's why it is facing the positively charged cation. All right, so that's how you will explain how you see the solvation and dissociation in this picture number 2. And I think that's it. It took longer than I wanted it to be, but yeah. Stop recording. Stop.